So what is exactly site investigations? If you want to construct something regarding or building or slope on highway, it's essential to know what's beneath the surface. That's the most important thing for the civil engineering or for the nation engineering or for the geologists to ensure what the construction facility is stable and meeting expectation during its life design. We must know the subsoil profile and the soil characteristic before we can carry out the proper engineering analysis. Of course, before you got at the moment you need to design geotechnical investigations, you will have architectural plan of the design, so you actually know what you're dealing with. Unlike most engineering materials, such as concrete or steel, soils have highly degree of variability associated with their properties. So in reality, when we speak about steel and concrete, we know a lot about steel and concrete. We know about a lot about man-made material. When we come to soil, soil's it's a bit difficult because we have so many changes, so many dramatical changes just in few meters, not just in soils and rock mechanics is the same thing. So it's a bit of challenge to predict actually how soil is going to behave, how rock is going to behave, and to actually go the parameters that we are going to use for design for the soil and rocks. Another reference is that we are typically have the luxury of the specifying grades of the steel or concrete that we have determined that will meet our requirements. When it comes to soil, we don't have that luxury because soil is it's just there. We just need to deal with it. We cannot say, oh yeah, that's a trend that we need to be soil. We cannot. We can just change our foundations or our design in general. So it's not that simple to just call it, yeah, we need a better quality soil because soil is already there. We just need to deal with it. So site investigation, also known as subsurface exploration or site categorization, is a process that can involve many tasks, including desk study, site visit, drilling, sampling, geophysical survey, lab testing, and a bunch of the in situ tests, depending on what kind of structure we are dealing with. So these tasks attempt to define the subsoil profile and determine the geotechnical characteristic of the different soils that we are accounting. So depending on the nature of the project and available budget, the site investigation can and should be between 0 and 1.5% of the total project cost. So basically, it will depend on the type of project. When we look at large scale projects such as dams or the nuclear plants, when we need to have really high factor of safety, we are looking more to have 1.5% of the overall budget. When we look at the highways, we are looking at the 1%, and for some apartment buildings, we are looking about 0.5% of the total project. That's general, but a good site investigation exercise should gather as much information as possible about site for a minimal cost. Uh, so the first stage in any case would be the desk study. Desk study would be like first stage of the site investigation program. This would require accessing all the available information, such as aerial photos, geological, topographical, and soil survey maps. Also, especially in the cities, you would have a range, especially if you're working more for one company, you would have range of the available data from the historical data from before. Also, depending on the country you are in, a lot of governmental agencies have already some data that they are gathering. For example, the moment where I am in Sarajevo, basically every time we did borehole to investigation to do something, we need to send all data to the government because they are making a database. So basically, if you need something, you can also withdraw it from the governmental registries. You need to pay for it a little bit, but it's a lot easier to plan actual geotechnical investigations if something is available. So today, also with all the online things you can find, such as Google Earth, you can find topographical maps on the internet. Find digital elevation maps. You can find lidar scans. You can find elevation maps. You can find a lot of hazard maps regarding landslides or the risk of landslides, the vegetation, and even the groundwater, depending where you are. Also, groundwater is one big thing that you can find with the government agencies, depending, saying again, depending on the country you are. For example, in Germany, you can just like go to the government agency and just type in where you are, and all the piezometers you can find, you can basically just scrape the data, so you don't need to pay for anything. But that's for Germany, so I'm not sure what how it works in your countries. Site overview involves site visit with camera to collect first-hand information on site access, expose overboard on the road or curbs, nearby rivers or streams, vegetation, previous land use, and the problems with the nearby structures. And those two stages can cost literally nothing, but play a really important role in planning and detailing site investigation program. So basically, if you start working as a geotechnical engineer or engineering geologist or civil engineer, you'll probably get quote request for quote to send prices for your geotechnical investigation. And first thing you need to do is basically go to the site. If you unknown with site, go there, check everything, go with camera, see first, look at the waters, look at the outcrops, and look at the structure of the nearby facilities. So if they're damaged, you're aware that something's not right. So generally, also the first thing you're going to use is going to be a geological map or the engineering geological map, depending what's available for you. Anyone here should have a geological map available. That's what every country already have. The scale is a bit different, but if you are looking in the United States, this for example Washington, you can find interactive maps for different states, which would include things as geological mapping, the landslide mapping, the risk of floods and stuff like that. So it's really important to just look at those things before you go to site, before you start making your report, and before you actually plan your investigation program. Also, one big thing that you need to look at is hazard identification. Depending on the place you are, you're probably going to deal with things like landslides, with things like rock falls, with the risk of the flooding, and usually there's a lot maps regarding all those risks. So sometimes it can be easy as I'm just going to Google it and find some stuff like this one here. This thing you can see on screen is basically landslide risk map, which would just specify, yeah, okay, this is the low risk area, this is the medium risk area, this high risk area. So basically going to design your investigation looking at the risk that you're possibly going to account. And one really important thing, and I would suggest doing it before sending the offer for geotechnical design, is site visit, because on site you're going to basically see the same. Yeah, but if you're going to do the desk study and stuff like that, you're going to have a lot knowledge before going to site. But on site, it's actually a place where you can see how what's reality. So as you can see on the photos, this like some of the damage on the places just because of the poor planning or poor engineering or unplanned use of land. And on the right side, you'll see like one really basic site visit for the geotechnical engineer or for the engineering geologist. It's just one rock outcrop, and you'll be happy to see rocks and not a bunch of soils or things like on the left side. So basically, when we gather all the available data, we know general geology of the site. We know what we need to build. We have all the graphs, all the drawings. You're going to think about planning of investigation. Later on, we are going to speak about what borehole is actually trial pit and stuff like that. But now I just wanted to show you how the actual just like basic plan looks like. So it's going to be like your base plan for actual design of the investigation. So every time you would know what's your boundaries of the building. So depending on the requirements from the standards your country is using, you're going to just place boreholes or trial pits or whatever kind of the investigation you want to have on a plan or where the proposed building is, and depth of the boreholes is going to be defined by you, but you need to meet minimum requirements that standards would require. For example, like proposal would be to have the borehole that is depending on building or whatever structure you're going to build. But let's look at the apartment buildings or skyscrapers. The borehole needs to be deep enough to cover influence of foundation. We were speaking about influence of foundation. That would be rule of thumb would say that three times width of the foundation would be influence of foundation. For example, if your foundation is going to be 3 meters, but your influence of foundation is going to be 9 meters deep, that is valid for the normal foundations you have. It's not valid for mats or for piles. Generally, for the piles, you would say that influence of the foundation is like 10 times of the diameter of the pile, or for mat, it would depend mostly on a height or thickness of the mat. But moving forward, we are going to first speak about what kind of types of geotechnical investigation we have, what kind of the tests we can do on site, and what's normal things to see on a construction site before we start in constructing. So the boreholes and trial pits are the most things that you would generally use. They are an integral part of any site investigation program. And boreholes would typically be between 50 to 75 millimeters diameter holes, the usual vertical holes that would advance in the ground to the depths as high as the 50 meters or more, depending on the purpose of the obtaining samples and in finding the underlayer soils. Generally speaking, it's also depend on the country you are in. For example, in Europe, if you look at the minimum requirements for the diameter of the sample would be 54 millimeters. So your borehole is not going to be less than 54, and you usually start at a lot larger diameter holes. We will start about like 114, 124 usually, and then we are gradually going to drop the diameter of the borehole. Also, depth is going to highly depend on the structure that you're going to use. For example, if you're of course if you're drilling for tunnels, you're going to drill a lot more, a lot deeper. For mines as well, we drill because for mines also you have an exploration drill hole that you're going to use for the investigation as well, but they can reach thousands of meters. For tunnels, it's a bit less, but generally speaking, the deepest one I saw in my life was in Frankfurt for one skyscraper that was 200 meters tall. Uh, we had around 80 meters of the depth of the borehole. So yeah, want to see is that your borehole is going to reach bedrock. So that's going to be bedrock is basically like you call it like mother rock, going to be safest piece of build, and you generally want to reach the bedrock. So of course, after the drilling, we are going to take samples, and the sample is going to be transferred to the lab to some series of the testing. Usually, that's water content, shear strength, attribute limits, consolidation, triaxial, and etc. Depending on the budget, of course, and depending on actual design that we are looking to get. Trail pits, also known as test pits, are a lot cheaper option. The thing is, with trial pits, you're looking to get around 4 meters or maximum, depending on your excavator and depending on your type of the excavating. But advantage of the trial pit is that enables you to do a visual inspection of soil, but also looking at the borehole, so you can do the same thing in borehole, depending on the type of the boring that you're going to use. Also for the trial pits, we can use and you can get samples. What we usually do is we would just cut a little bit of block, and we will send it to the lab, from the floor or from the wall, depending on which depth we are looking to get. And we're going to push our pocket penetrometer or the vein shear strength. We're going to speak about that more in the future. And we're just going to send it to lab, and the lab is going to prepare the sample as they wish. Uh, First one, as you're going to use most, is going to be usual drilling of the boreholes. As you can see on the right side, that's just one basic picture how the boring actually looks like, and there's just a bunch of samples that you're going to use depending on the type of drilling that you're going to use. So drilling and in situ testing and sampling go to hand. Trial pits or trenches are inexpensive and generally adequate for the shelf depths or some preliminary investigations. So just for some feasibility studies, don't go for the skyscraper design with just trial pits. Yeah, sure. Um, they enable visual inspection of the stratification of the soil near ground level. When it comes to the detailed soil exploration, it's necessary to drill some boreholes to desired depths and collect samples of the various depths. Of course, there's a different kind of the drilling that will depend mostly on you and mostly on budget. What usually we have two methods, going to be destructive and not destructive method. Destructive method would be auger method that basically would damage your samples. You wouldn't get you will get usual samples. It would work in some non-cohesive ground, such as sand or gravel and stuff like that. But if you are looking to have the core, like clay material, really soft material, or rocks, we are looking to get non-destructive methods of the drilling that would give us the full core as it's shown in photo. Generally speaking, the full coring would basically be like one hollow pipe that would just drill around soil, and soil sample would just stay inside of the rod. So basically, you can inspect your soil as is in nature form, and you can take samples directly from one. So generally, trial pits, as you all know, can be excavated manually, or you would mostly do it with the excavator. The one important thing about trial pit: do not walk inside if it's unprotected. As you can see on the right side, there's one guy in a trench in a purely cohesive or not cohesive soil. It looks like sandstone. He's doing mapping there. He's probably a geologist, but the trench is probably around 4 meters deep, and he's like what, not more than 2 meters. And those things are extremely dangerous. And now, while we are going to the field and field tests and stuff in general, I want to speak more about health and safety on sites, because it wouldn't be the first time that something like that could happen. People got injured, people got hurt, people got killed on sites. It's really important to be aware of the PPE on site that you need to use, and don't put yourself in danger. If you, no one can make you, no one can make you to do it. So in the middle photo, you can see how the actually needs to looks like. If you're going to deeper trench or to deeper trial pits, you need to support it first, and then you can inspect just the walls of the pit. Generally speaking, you're unlikely to be asked to do such thing, because most of the things you can just see from the surface. Just going to take photo. You're going to go there with your measure tape, do pictures, and if you need to take samples, go there after it's protected. Usually, we would say that if it's more than 50% of your height, don't go in the trench. When you speak about sampling, in granular soils, it's very difficult to obtain samples in general. Undisturbed samples would be almost impossible. There is, of course, special techniques that would be freezing of ground, using resin, things like that. But that would be very expensive, and it's usually not required. There's just few projects in this world that did require to have sampling in the granular soils. Therefore, the common practice is rely on in situ or field tests for determination of the geotechnical properties and the characteristics. And if necessary, we can reconstruct all the samples in lab using some kind of material, some kind of method. Those are laboratory samples prepared to specific packing density to match that we had in situ. So we are mostly going to speak about cohesive soils such as clay, such as silts, and stuff like that, because easier to sample it. It's you basically you can get samples. It's very important to have those samples. When we speak about sampling in a cohesive soil, we looked first at the to get Atterberg limits, water content, specific gravity, etc. That would be commonly known as the index properties, and those things can be removed samples and from the training. So in reality, if you're looking to get Atterberg limits and water content and stuff like that, we don't need to have undisturbed samples. We can just send any type of sample that we would get on site. It can be disturbed, it can be damaged. Just what is important to have natural water content. So just stretch it with foil and send it to lab. Generally speaking, we spoke about those tests before. If someone of you been on a lecture before with me, when we speak about a consolidation test and a triaxial test, they would require really good quality and undisturbed samples, which would be mostly in clay and silt. And if you are looking to get those samples as perfect, we would need to use tube or block samples. But tube samples we could get from the boring, or block samples we can get from the surface. While we can basically cut it from the surface if we have a rock outcrop, or from the trial pit, as we said before. So tube samples are obtained by pushing thin walled metal tubes about 75 to 100 millimeter in diameter and 600 to 900 millimeter length into soil in desired depths we are looking to get. Under exceptional circumstances, we can use really large diameter boreholes and we can take the samples, but only to do limited depth, because they can be really expensive and we're more likely looking to get just block samples from there. So especially in a cohesive soil, any disturbance during the sampling can destroy the fabric, which can result of the underestimating of the strength of the stiffness of the soil. Therefore, it's highly desirable to minimize the soil sample disturbance during the sampling and later during the handling and transportation to the lab. Disturbance of the soil sample comes in two forms. First would be significant stress relief, because especially when you're getting samples from some greater depths, such as 20 meters, 30 meters from soil, or hundreds of meters from rock, what you can see is basically when you put sample from the ground, it was in one state of the stress. We had some vertical stress, we had some horizontal stress that was captured in the sample, and at the moment you pull it out on the surface, those forces are not really there. Those vertical stress is not really there. Horizontal stress is not really there. So the sample would relax. Generally, it's really hard. It's really hard to minimize those stress reliefs. But what we can minimize is the mechanical distribution of sample. Especially, we can get thinner walls of the sample. So that would generally minimize the deformation of the sample. So this is basically one basic thing that you would generally use in a sampling of the soil. It's called Shelby tube. It's basically tube that you would put on your rod on your drilling rig. You would just push it to the soil until it's full, and after that, in a tube there's PVC, usually the PVC pipe that would capture the sample. You would open the tube, or they're reusable. You would open the tube, you would just pack your sample in oil or whatever kind of of the package of the samples your lab is going to use, and you would reuse your shell with sample to get more results and to get more samples. Moving forward is just one graph that would show effects of the stress relief on the shear strength and stiffness of the samples. As you can possibly see, those points there would be laboratory results, and those lines there would be in situ testing from pressometer, dilatometer, and stuff like that. Generally speaking, as you can see, we have a lot larger results in situ testing, and a lot smaller in lab testing, just because of the relief of the stress. Generally speaking, we are not going to make mistake using the undisturbed samples that we covered in lab, but those results are going to be a bit conservative. Generally speaking, when you look at someone who's just starting career, I would suggest to go with the conservative results more than take risk, because you probably are not really aware of all the risks that are hiding there. One really important thing in the ground is also water table. The location of the water table play a key role in the computing effective stresses. Locating of the water table is objective of the site investigation exercise. This can be done observing the water table in your borehole that you drilled 24 hours after drilling, when everything is stabilized. Depending on the structure you're going to use, you're probably going to monitor your water over the year if the project is long term, just so you can see what's the maximum groundwater level that you can expect. Because the water generally has this huge influence of the stress of soil, and huge influence of based on strength of soil. Alternatively, the water table elevation can be also measured from the nearby wells, because generally speaking, the water table is most likely a flat line. So if you have well close to your site, and if on well you can see the water depth is 10 meters, it's most likely that your water table is going to be 10 meters on your site as well. So that's going to be a good enough result. So also it's important to actually have water samples. We would take water samples to the lab to do some chemical analysis, especially for the aggressivity of concrete. If you're going to have foundations that they are going to, in any time of design life, is going to be in contact with water. For example, sulfides have a lot of aggressivity properties on the concrete and on foundations. So basically, if you see something like that, if you see that your water is going to be aggressive on your foundation, you're going to basically just redesign your concrete, and you're going to take in account aggressivity, and you're going to change cement and usual stuff. After we got all the drilling or the trial testing, what you're going to do is we are going to go to office, and we are going to do something that's called logging of boreholes, or logging of trial bits. So that's basically drawing of everything that we saw on the site, we mapped. We spoke about soil categorization on the first lecture, if someone of you remember. So we spoke about all those letters that are here, all those descriptions that you can see here. So basically, this is just from one software. It doesn't matter how it looks, but what you want to see on your logs is going to be depth, or it's going to be elevation, depending on what kind of project you're using. The casing, if there's any, usually if you look at the boring in the gravel or sand, you would have casing. The core bit that you use, sampling type, returning water or losing the water in some cases, geological description that would just cover some basic stuff you saw there. The water level is, if there's water level there, 5-meter depth, you're also going to see the dates of the water levels, because it will change eventually. It will change over time. UCCS classification of soil, as we spoke to the first one. The standard penetration result is going to be next slide, and all those things there are just laboratory results, as we spoke in the previous classes. We're also going to put there all the projects that the name of your borehole, because you're going to have different names for the boreholes on the site, and the one really important one is going to be location in coordinates, because you're going to come back to that borehole, is going to use it eventually in your future. So it's really important to have it in your database with the coordinates. So when we look at the in situ test, in situ test consists of the intrusive inserting device into ground and measuring its resistance to or penetration of the formation, which is then translated into strength and the stiffness parameters as the soil parameters or the rock parameters, regardless. The most common one of the situ test is the penetration test, or the, for example, standard penetration test, or the cone penetrometer test. We're going to speak about those things just a bit after, where an open-ended sampler or the solid cone is driven or pushed into ground, and the resistance of the penetration is measured. So this resistance is after that translated to the strength and the stiffness of the soil, and about 80 to 90% of the situ testing exercise worldwide consist of the penetration test, such as the standard penetration test or the cone penetration test. And I never saw a site that we didn't had standard penetration test before. So you're most likely going to see that in you're going to work on sites, on building sites. From the penetration, the resistance at any depth, the shear strength parameters, for example, CU, which would be underlying cohesion, and the soil stiffness, which would be E, or Young modulus, if you what you would use for the concrete or steel, can be determined. Moving forward with SPT, we would just call it that standard penetration test. The standard penetration test, there's just standard that is used in USA. Every other country has different standards, but by the end, all of them are basically almost the same, especially for those really basic tests. So SPT is one of the oldest and most commonly used in situ test in geotechnical engineering. So nickname of the SPT was original development in the United States in the early 19th century because it was used for sand. So basically the number of balls would require to achieve 3 subsequent 150 millimeters penetration is recorded. The number of balls required to penetrate the final 300 mil is known as the blow count, penetration number over n value, and it's denoted by n. The blow count for the first 150 millimeters is in order to affect of the disturbance of the bottom of the borehole. Generally speaking, we have most likely 2 different SPT types. What is most likely used in USA is going to be this one. It's called split spoon standard penetration test. And in Europe, if you look at Europe, we would most likely use those ones in a clay zone and cohesive zone, and these cone ones in a sand and non-cohesive soil, such as sands, such as gravel, and stuff like that. So basically, what you would have is you would put cone or split spoon on your rod, on your drill rig, and depending on standard, you would just push it on the ground just to touch the bottom of your borehole, and you would lift most likely mechanically, because that's what we are doing at this moment, and most of the drill rigs have just mechanical integrated SPT. So what you would see is that machine is going to pull it rod with SPT cone 1 meter from the bottom of the hole, and it's going to drop for 1 meter of height to the bottom of the hole. So basically, because it's constantly dropping, of course, your soil is going to deform by dynamic impact, and what you're usually doing, you would divide your rod on 3 times 15 centimeter scales. So what you would do is you have first 50 centimeters, you would count the number of the balls that would account there. For soft soil, it would be 3 or 4, something like that, or really stiff soils would be 40 to 50. And you would just ignore the first 15 centimeters, and then you're going to repeat the process. So after that, you're going to record next 15 centimeters and next 15 centimeters, and you would get basically two numbers. And for example, that can be 17 and 18, and that would be in total 35, and your number n would be 35. So you would say that your standard penetration test result would be 35. Generally speaking, that's not the only thing that you're going to write, because the variability associated with the choice of the FPT equipment and test procedure worldwide, while various correction factors are applied to measure blow count n, as we already spoke about. Two most important correction factors is going to be overburden pressure correction, CN, and the hammer efficiency correction, EH. The blow count corrected for overburden pressure and hammer efficiency would be expressed as the N of 16 that you would usually see for all the correlation you're going to use for the FPT. That would basically include this number here is going to be overburden pressure that you can calculate. This one here, the sigma prime, you can see here is basically effective stress. Effective stress you're going to calculate based on depth that you used your SPT for. And for that, you're also going to need the water table, because you're going to subtract the water table from this one here, and you're going to get lower overburden stress. And those two factors there are basically efficiency correlation that will depend on the type of equipment you use, the diameter of the equipment, height of the depth of the borehole, and stuff like that. So you're basically going to depend on the equipment you're going to use generally. So when we look at this number here, it's going to be number of the penetrations we just spoke about. So you have a little bit of table that you can just divide your soil. So very low soil would be everything to 4 blows per 30 centimeters. 10 would be a border between loose and medium dense and dense and very dense. This is drawn for the non-cohesive ground, such as gravel and sand. For the soil, it would be, for the clays and cohesive ground, would be different, and it's most likely written in your national standards. For example, Eurocode 1 that we use in Europe and ISTM that is used in USA would have specified those tables for the cohesive and non-cohesive ground. Also, what you can see in standards, it would be the most basic correlations that you can get from those tests. Moving forward, we are also looking to get a site static cone penetration test. Basically, the static cone penetration test, also known as a Dutch cone penetration test, because originally it was developed in the Netherlands in the early 19th century, and can be used in most of the soils. What we usually see in Europe is mostly used for the softer clay, or the place where we don't have a lot of the non-cohesive ground, such as huge, sand and gravel. The split spoon sampler is replaced by the probe that can consist of the solid cone with a 60 degrees angle, with the base area of the 10 square centimeters, attached to the drill rod with the friction slave having a surface area of the 150 square centimeters. And the probe is advanced in the soil, often jacked in by truck at the rate of the 20 millimeters per second. Looking in the modern area, at least what I have experience with, we usually are not going to jack it on the truck. You're going to have just a smaller machine that's going to push rod in the ground, and you are going to use you can use for SPT, we can use it for CPT, which would be core penetration test. We can use it for the dynamic test, medium dynamic penetration test, the high weight dynamic penetration test, stuff like that. Because on one machine we can cover a lot of things. Also, generally today, uh, we can see that test is going to measure also the pore water pressure. That's going to be a really important factor in design. And also because of the pore water pressure, you would basically by pushing rod in the ground, you would know where your water is and where your water level is. Here, all the three measurements are taken in the same time. The cone that's pushed in the ground would measure the cone resistance, that would be QC, the sleeve friction, FS, and the pore water pressure, which would be U in the general formulas. So rule of thumb would be the granular soils have high cone resistance and low sleeve friction, while clays have high sleeve friction and a low cone resistance. And the friction ratio at any depth you can calculate basically just using this formula. And this is a graph of the classification of the ground using cone resistant QC and the frictional ratio you're going to calculate based on the sleeve friction as well. So basically, as you can see, the cone resistance is a lot less in a sensitive fine grained soil and the biggest in a gravelly sand to sand. And when we look at the really fine, stiff grained, or consolidated or cemented soil, we are looking to have a huge friction ratio and a huge cone resistance. Generally speaking, this would be basic. Sorry, this would be basic result that you would get from the CPT. I really like CPT, and it's really you can get a lot of data just from CPT, and it's basically usually same price as a boring. It's really easy to use, and you can get a lot of data as you're going to see right now. So the first one is going to be cone resistance, that is going to be measured just by pushing a cone in the ground. Next one is going to be sleeve friction, and third one is going to be pore pressure. So basically, because if there's no water, your pore pressure is going to be zero, and at the moment you get pore pressure more than zero, you can say that you have water table level just there. So also based on all those three factors with a lot of calculations, this was from one Greek software called Geologisky. If you're going to work with a CPT, you're going to heard about this guy. This is Robertson. He's basically expert in CPT, and he worked a lot with the CPT. He had plenty of correlation for the CPT and another properties, another strength properties of the soil that you can get over the CPT performance. So this is basically just basically log of the CPT. So based on all those three parameters, you can get your log, and you can define what kind of the soil you're going to account by excavating thereafter, and you can use it for design. Also, what you can get based on correlations, you can get the probability of the soil, you can get SPT number, as we spoke before. As you can see, this is really soft clay material. This was one project I worked before. It was for one airport, and basically for 30 meters of the airport we had like just mud. So as you can see, we had a really soft material based on SPT. Also, when there's enough data, you can calculate the Young modulus or the elasticity modulus. You can calculate relative density, and you can calculate the friction of angle. That's really important for the designs. Also, what you can get is the constraint modulus that you would usually get from the odometer. You can get shear modulus that you could get from the shear test, shear strength, which would be really important for designs, undrained shear strength ratio, and the OCR. OCR would be over consolidated ratio, which would mean that soil was exposed in the history to some greater stress than it's now. A lot. I just said you can get a lot of results just from the CPT, and it's really good test. And I really like to see you using those tests in your future. You can get shear wave velocity, which you would usually get in with the geophysical investigations. Get state parameters, which be this number here. In situ stress ratio, which would be these lateral coefficients that you're going to use generally for design of the retaining walls. Soil sensitivity, which is basically a parameter that you would get from the attribute limits, and effective friction angle, or the peak phi in degrees. Also, what you can get directly from the software just using the CPT, you can get bearing capacity of your foundations. So basically, capacity of your foundations depending on the width of the footings, and this is the usual things that sorry, the usual things that you would be put in a elaborate or stuff like that. So generally speaking, in the future, we are going to speak more about more in situ test. That would be vein shear test. That's one test that you're going to do every time on a field. You're just basically like really handy this peak. You can just like can pick it and go and use it on the field. Going to be pressure meter test, dilatometer test, plate flow test, and some of the geophysical tests. We're not going to speak a lot about geophysical tests. We are just going to cover some basic ones, so you can just get a feeling what you can use. Also, after that, we are going to speak about general principles of the soil mechanics, so you can understand what's actually stress, what's actually the pore pressure in the soil. I'm not sure what's your background. I'm not sure did you cover those things before, and we are going to speak. After that, we are going to speak about all the results we are going to get and how to actually make designs, on based on that. So I will just leave those extra 10 minutes we have for the questions, because last time I did lecturing, we had around 15 or 20 minutes just for questions. So if someone have questions, please raise your hand or speak or write it in a comment section.